Hey everyone! Today we're going to learn about exponential and log functions. One of the things I like to do when I teach is to learn new material by jumping off from old material that you already know. So let's do that in this case. It's kind of good to, I think of it like wading into the water where you keep one foot on the shore and you venture off with the other foot. So there's the line, there is a line. Let's call it f of x is equal to 2 times x. Okay, so there's a line with slope 2, and it goes to the origin. So when x is 0, y is 0. And notice that as x goes from 1, 2, 3, 4, that the value of the function does what? The value of the function goes 2, 4, 6, 8. In other words, every time you add 1 down here, that means that you add 2 up here. So you can think of it this way, that when you go from one integer to the next integer, you add 2 in order to continue on. That's of course why we mean that the slope is 2. That if this changes by 1 unit, this always changes by 2 units. So you can think of it as just adding 2 as you go. Okay, you add 2 as you go. So that's 2 times x. Now let's graph g of x, let's call it, is equal to 2 to the x power. Okay, so in this case, when we let x and f of x, here it was 0, 1, 2, 3, and this was 0, 2, 4, 6, and so we added 2 each time. Okay, we added 2 each time. Now, as we think through what this is going to look like, what's going to happen? If x is 0, then 2 to the 0 is 1. Okay, we talked about that earlier. If x is equal to 1, 2 to the first power is 2. Then when x is 2, 2 squared is what? 2 times 2 is 4. If x is 3, 2 to the third is 8. When x is 4, 2 to the fourth is 16. When x is 5, 2 to the fifth is 32. If we take negative numbers like -1, 2 to the -1, remember what 2 to the -1 means? It means 1 over 2 to the first power. That's 1/2. What about 2 to the -2? That's 1 over 2 squared. So that's going to be -2 is going to be 1/4. If you have a -3, 2 to the -3 is 1 over 2/3. 2 cubed is going to be 1/8. Okay? So, let's see what this graph looks like. This gave us a straight line. If we connect all these points, we're going to get something that looks like this. Get something that looks like that. It's going to grow very, very fast. Notice how fast this grows. 2 to the 5th is 32. If you went 2 to the 6th is 64. 2 to the 7th is 128. It not only grows much faster than 2 times x, it also grows much faster than x squared. If you think of putting 10 in for each of these, 10 squared is 100, but 2 to the 10th is over 1,000. It's 1,024, and it only keeps getting bigger and bigger after that. So it grows very, very fast. So that's one thing you should realize about an exponential function. This is an exponential function, and the one thing you should realize about it is that it grows very, very fast. Another thing you should notice about it is that it never goes negative, because look what happens when you stick in negative numbers. Here, when you put in negative numbers, -3, you'd get -6. Okay, here you put in negative numbers, and it's just 1 over the positive number. See that? So the domain is the whole real line. You can put any number you want to in the world for that. The range is all positive numbers, not even 0, just the positive values. Very good. So that's what this one looks like. What if we were to compare it to, let's get another color here. What if we were to compare it to h of x, which is 3 to the x power? Okay, can you picture in your mind, even before I give the values, what it's going to be? 3 to the 0, let's just make another column here. So this is going to be h of x. And h of x, h of 0 is again 1. You stick in a 1 here, you get 3. 3 squared is 9. 3 cubed is 27. 3 to the 4th power is 81. That's 9 times 9. 3 to the 5th power is 243. That's as far as I can go. Multiplying by powers of 3. Now if I take negative values, it's going to be 1/3, 1/9, 1/27, and so on. So as fast as this thing was rising, 3 to the x is going to rise even faster. Okay, it's going to go up even faster, and it's also going to go down even faster. So it's going to look like that. So here's your h. Okay, first one was g, and that one is h. Okay, and you can do this with any number. Okay, same thing. Notice that it's going to be growing very fast. It's always positive. Should have this one in mind. Let's do another one. Let's do 10 to the x. I choose 10 to the x because that's one that's often used in the world. And so let's see what it looks like. Okay, 10 to the 0 is 1. So this is going to be, this is k to the x now. And 10 to the 1st is 10. 10 squared is 100. These are easy to do. 10 cubed is 1,000. 10 to the 4th is 10,000. 10 to the 5th is 100,000. Keep multiplying by powers of 10. 1/10, 1/100th, 1/1000th, and so on. So the key thing to notice, going back to 2 to the x as an example, here we added 2 each time. Here, notice we multiplied by 2 each time. See that? So here you're adding 2 to get to the next one. Here you're multiplying by 2 to get to the next one. So when I have my original g of x, and I wanted to go from 1 to 2 to 3 to 4 to 5 and so on, every time I jump to this next value, the value of the function, in this case, grows by 2. In this case, the value of the function grows by 3. In this case, the value of the function grows by 10. So here you're at, for 4, you were at 10,000. Here you're at 100,000. So obviously I don't have this graph going up nearly fast enough. I would need a much taller board in order to do it. So I can just kind of, not even approximate, but just give something that gives the idea. So there it goes like this, and again, it goes down there. So it grows very, very fast, and it goes down very, very fast, and it keeps on going. You can keep on going forever here, and these will just keep on going farther and farther, and it just goes very, very high. Okay, so that's 10 to the x. Okay, let's do one more, and I left red for this one, and we'll call this L of x. And I'm going to choose a number now which is between 2 and 3 in size. It's the number e. You remember the number e? We talked about that a little while ago, about 6 or 7 lessons ago maybe. And e was a number roughly 2.71, something like that. And so e to the x is going to be a graph that lies between 2 to the x and 3 to the x, because since e lies between 2 and 3. And so it's going to be a graph that would look like this, and also go down here. Okay, so it's kind of, they're all smushed together. That one's going to be e to the x. Okay? So why do I choose that one in particular? It turns out that in many ways this is the most important one. And I'll show you in a little bit that all these other ones can be written in terms of e to the x. So that way you don't have to remember, kind of think about all these. You just work with rules of e to the x and it makes things kind of simple. Okay? Let's do one more before we go. And this one is going to be, let's see, I'll go m of x. And let's just let it be 1/2 to the x power. Okay, 1/2 to the x power. So this is m of x here. And so now let's see once what happens. 1/2 to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 squared is 1/4. 1/2 cubed is 1/8. 1/2 to the fourth power is 1/16. 1/2 to the fifth power is 1/32. Remember, that's easy to understand because 1 to the x over 2 to the x is just the same as 1 to the x over 2 to the x. And 1 to the x is just always 1. And so that's just always going to be 1 right there. And so it's 1/2 to the x. See that? So while these things got bigger, these are going to get smaller. And so 1/2 to the x, similarly, if I stick in a negative number, 1/2, what's 1/2 to the -3? That's going to be 1/2 to the -3 power. And if you flip it over the line, then you change the sign. So flip it over the line and you change the sign. So 1/2 to the -3 is the same as 2 to the third. So this is going to be 8. It's going to be 1/4, 4 and 1. Oops, 4 and 2. Like so. Okay, let's do one more. 1/2 to the -2 power is 1 to the -2 power times 2 to the -2 power. This is always going to be 1. And 2 to the -2, you flip it over the line and change the sign. So that's 2 to the second, which is 4. So what's this one going to look like? This graph is going to be kind of the flip of this graph. It's going to look like you just flipped it around the line around the y-axis. It's going to go up like that. So here's this function. This is 2 to the x. This is 1/2 to the x. See how they compare? You can just think of flipping it around the y-axis there. And similarly, 1/3 to the x would be like this, and 1/10 to the x would be down like that. They'd all go like this. Okay? So notice that 2 to the x is growing very, very fast. 1/2 to the x is getting small very, very fast as you take larger and larger values of x. Okay? Very good. Okay, I really want to do one more now that I think about it. I just kind of mentioned it, but what about n of x is equal to just 1 to the x power? 1 to the x, that's boring. 1 to any power is just going to be 1, so that's just going to look like this. So there's 1 to the x. See that? So, key idea here. If you give me a number bigger than 1, it doesn't even have to be as big as 2. It can be 1.001. You give me any number which is bigger than 1 and take it to the x power, it's going to grow like this. It's going to grow up bigger and bigger because as you take a number bigger than 1 and keep multiplying it by itself over and over again, it just keeps getting bigger and bigger like this. So it's going to grow up and it's going to go down in that direction. You give me any number that's less than 1 in size, like 1/2 or even 0.99. You take a number that's less than 1 in size and you keep multiplying it by itself over and over and over, it's going to get smaller and smaller. So that's going to be one kind of like this, which just keeps getting smaller and smaller and smaller, goes to 0. And finally, right in the middle of both of those, if you just take 1 to the x, it doesn't do either. It doesn't get bigger, it doesn't get smaller. It just stays the steady course. Okay? So there you go. And that's why you can see, by the way, since the whole COVID coronavirus situation, you're concerned about how many people a person infects. You want the number of people that any individual infects to be less than 1. If it's bigger than 1, here's what happens to the number of people who get COVID. It goes up like this. If the average number is less than 1, it's going to die out like that. And so that's why it's so important for people to wear masks, to socially, physically distance, kind of keep somewhat isolated, just to be careful, and try to make sure that people don't start passing it on. Because if every person passes it to 2 people, see, it's just like this graph. Here you are now, everyone passes it to 2. So say a week later, if everyone's passed it to 2 people, now this is twice as big as this. If everyone passes it to 2, now these are the number of days, then you're going to have twice as many here as here. If after the next day or the next week, whatever the unit of time, everyone passes it to 2, it's going to keep doubling. So it's very important that you want it to go down rather than go up. Okay? That's why an understanding of mathematics helps you appreciate some important stuff in the world. Okay? Very good. Okay, now let's get rid of all this. Key thing again, I just want to emphasize it. This grows very fast as you go from here to here. This one doubles. The other one triples. This grows by 10. Whereas here you add 2, here you multiply by 2. Okay? Okay. Now, as I say, the most important of all those was e to the x. So let's graph that one again. There is the function. Let's call it f of x is equal to e to the x. And so here is 0, here's 1, and so this would be e to the first power right there. Here's 2. So this value here would be e times e, or e squared. Here's negative 1. So this value here would be e to the height would be e to the negative 1, which is the same as 1 over e. Okay? And so on. Those are the heights. Okay? Now, certain functions have a very important property. They are said to have an inverse. Here's the idea of an inverse. Remember what a function looks like? I think of it like a machine. You put a number in, the function does something to it, and spits a number out. Okay? Here's what the inverse does. It says, hey, before you look at that number, put yourself on a conveyor belt, and so this number here goes into this machine, f of x goes into this machine, and this machine takes whatever this takes an x and throws out f of x. This machine takes the f of x and gives you back the original x again. It undoes whatever this function does. Okay? This function, the way you write it, is f with a negative 1 there. It means that it undoes what this one does. So if you were to use symbols of functions, you'd say that f of x, you'd first take that and then you stick that into f inverse, and by the time you're done, you get your x back again. Or similarly, they undo each other. If you first take x and you put it into f inverse, and then you take that and you put it into f, again you get your x back again. They undo each other. Okay? And e to the x, along with the other exponential functions, all have inverses. And there's a special shape that the inverses have? It turns out that if you graph the function, you can get the inverse by just flipping this graph over the line y equals x. There's the line y equal x. So if you think of making this in really wet ink and then folding the paper right along there and fold it here, what would it look like? It turns out this is what it's going to look like. Can you picture it? It's going to grow up like that. It's going to go down like that. Okay? So this is the function e to the x. This is the inverse of it, and the inverse of it has a special name. It's called the natural log. The natural log of x. Okay, it undoes what this one does. So in other words, if I take the natural log of e to the 7, well, this took 7 and gave you e to the 7, and this gives you back the 7 again. They undo each other. Or if I say e to the ln of 7, they undo each other. You get your 7 back again. They undo each other. Whatever this does, this undoes it. Whatever this does, this undoes it. And so you just get your number back again. Okay? Okay, I decided to draw this a little bit nicer. And so here it is again. Let me just say it one more time. Here's the graph of e to the x, and then here's the graph of its inverse, which is the ln of x. And since they undo each other, that means that whatever point is on this graph, the kind of flip point is going to be on this graph. They flip around the line y equal x. So since the point 0, 1 is here, the point 1, 0 is on this graph, which means that the ln of 1 is equal to 0. Since the point 1e is on this graph, the point e1 is here, which means the ln of e is equal to 1, which we already know because the ln of e to any power is just equal to that power, and this is e to the first power. Since 2e squared is here, the ln of e squared is going to be equal to 2. So they just undo each other like that. Okay? That's the key relationship between an exponential function and its accompanying logarithmic function. And another thing to notice is that since this thing grows very, very, very quickly, this thing is going to grow very, very, very slowly. Okay? Let's I tell you what, let's use the same graph, and instead of thinking of it as the ln graph, now let's do it as 10 to the x. It's going to have the same basic shape. So this is going to be 10 squared. 10 squared is 100. 10 to the first power is 10. This is going to be 1/10. And so on. And so these are going to be the points 100, which is 10 squared, 2. Here's the point 10, 1. There's the point 1, 0. We could think of this as being the point 10 now. So now, instead of the ln, the name, the inverse of this function is called the log base 10 of x. They're the ones that undo each other. In other words, the log base 10 of 10 to the x is just x. They undo each other. Or 10 to the log base 10 of x is equal to x. Again, they undo each other. Okay? So, in other words, you take a very, very large number, like 100, and put it into this graph, and notice what you get out. You just get out a 2. If you put in 1,000,000, here's 1,000,000, which is 10 to the 6th, all this is going to be up is 6 units high. So it grows very, very, very slowly. This one grows very fast. If you put a 6 in here, you're all the way up to 1,000,000. If you put 1,000,000 in here, you're only all the way up to 6. Okay? And that, by the way, is why we will get into this in the next video. But that's why logarithms are used whenever you want to deal with something that grows very, very, very large. When you have a large difference in the size of things, we'll talk about that. It's because it grows so slowly. Okay, so that's key. Okay, so here's a little bit of good news, and that is that we have all these functions. Remember what they all are? Let's get rid of this right now. And let's think of what they were again. We had 2 to the x, and 3 to the x, and 10 to the x, and e to the x, and 1/2 to the x. And all of these had a shape that looked like this, whereas this one, when you took 1/2 to higher and higher powers, it had a shape that looked like that. So, something to notice then that's very important. If a is greater than 1, such as these right here, then y equals a to the x is going to have that shape. If a is between 0 and 1, which means it's less than 1 in size, then a to the x is going to have that shape. Okay? If you take a number less than 1, it's going to decrease as you go. If it's greater than 1 in size, it's going to increase as you go. Very, very important. And that's why, remember, we said that the COVID, it's so important to have a number less than 1 in size so that as time goes on, it decreases rather than increases. Okay? Another important thing to notice here is that 1/2 to the x power can be written as 2 to the negative 1 to the x power. And now remember, you can multiply those exponents. So that's 2 to the negative x. So another way of writing this is 2 to the negative x power. They both are exactly the same thing. They both have that same shape. You can either take a number which is greater than 1 and take it to the negative x power, or you take a number that's less than 1 and take it to the x power. Either way, you're going to have that same shape. And I guess even another way of thinking about that is that that's the same as 1 over 2 to the x. So as 2 to the x gets big, 1 over that is going to get small. So there's just all sorts of ways to understand this. Okay, here's yet one more thing I want to show you. I'm going to erase that line right there, and I want to show you this. A to the x is equal to e to the ln of a, because e to the ln of a is the same as a, agreed? They undo each other. E to the ln of a, all to the x power. And now I can multiply these exponents, and so that's e to the ln of a all times x. Okay? So it's kind of nice because that shows what that really means is that I don't have to worry about all of these graphs. I can just concentrate on the graph of e to the x. Here's the graph of e to the x and its inverse, which is y equals the ln of x. Okay, so here's e to the x and the ln of x, and now you can just concentrate on that. Let's see why. Let's see why. If you take some value like 2, which is greater than 1, you take a value which is greater than 1, notice that the ln of a number which is greater than 1 is going to be a positive number. And if you take e to a positive number times x, you're going to get a graph that looks like this. Okay? On the other hand, if you take an a which is between 0 and 1, here's between 0 and 1, and you take the ln of that, the ln of that is a negative number. And if you take, this is where you have a positive value. Here, if you take e to a negative number, it's going to look just like this. It's going to have a graph like this. So the key is that Here is e to the kx where k is positive, and here is e to the kx where k is negative. Okay, and you'll see that in your book too. When your book has a population problem, then you had e to a positive number times t, and so you had population growth. When you had exponential decay, then you had e to a negative number times t, and you had something that decreased over time. Okay, so that's an awful lot of material, and so there's your first shot at it, and then you can get it from your teacher and you can read it from the book, and we'll do it again in the next lesson as well and give you a chance to really let it sink in. Okay.